Hello everyone, my name is Yoshiaki Mita and I'm a third grade student at Mita International School of Science. And today I'll be presenting my presentation, Biodegradability Assessment of Wastewater, a novel microbial fuel cell-based BODQ sensor. These are the table of contents, and I'll first start off with the background and my research objectives. To start off, the water crisis is a major environment issue that is currently challenging the world. And up to now, it is known that more than 700 million people suffer from water shortages. 48% untreated wastewater are discharged to the environment, and over 1.4 million people died from related diseases. To counter this, we use wastewater treatment plants. The wastewater treatment plants we rely on are critical infrastructures for keeping our water clean. And these plants mainly use biological processes, and their performance mainly depends heavily on the wastewater's biodegradability, which we measure using an indicator called biochemical oxygen demand, or BOD. BOD is a crucial quantitative indicator to quantify the present amount of organic matter in wastewaters. But the problem is, the current method, or the standard method for measuring BOD, called the BOD5 test, takes 5 days to get a result. And this is far too slow for the real-time adjustments needed to run a treatment plant efficiently. Therefore, we need a better alternative for rapid BOD detection technology. A much better alternative is a microbial fuel cell, or MFC-based sensor, which is a device that uses microorganisms to directly convert organic pollutants in wastewater into usable electricity. It consists of a chamber, bioanode, air cathode, and resistance. Through the oxidation process, in the anode, the released electrons travels through an external circuit, creating a current, while the electrons at the cathode reduces oxygen into water. The total amount of electrical charge generated, which we call Q or Coulomb, is calculated by integrating this current over time. And this total charge Q is directly proportional to the amount of organic material the microbes have consumed. From there, we can use a formula to calculate the BOD value, which we refer to as BODQ. The MFC-based BOD sensor was proposed as a better alternative method for BOD detection due to their high sensitivity and changes in concentration and their characteristics that enable real-time responses. This enables reducing the detection process to approximately 1 day from 5 days, enabling real-time detection. However, MFC sensors still face challenges. First, they tend to systematically underestimate the true BOD values. And second, while a day is much better than 5 days, the detection process could still become shorter. This led to my research objectives, to identify optimal resistance and shorten detection while ensuring reliability. And to do this, the effects of external resistance were investigated, and the refinement of current time curve analysis method was proposed. Next, I'll be moving on to experimental materials and methods section. For my experiments, which are conducted at my house, I used 4 MFC cells kindly provided by the School of Environment at Tsinghua University in China. I created artificial wastewater using a specific receipt so that I would know the exact starting concentration of organic matter. I then tested 4 different resistance levels, 1000 ohm, 500 ohm, 100 ohm, and 10 ohm, to see how each one affected MFC's performance. I'll then move on to results and discussion. After running the experiment, we can see the effects of different resistance on the BODQ. Through a comparison of 4 different resistance, it is clear that 100 ohm provided the best balance of sensitivity and linearity, with a sensitivity score of 0.197 and a linearity score of 0.993. While 1000 ohm and 10 ohm resistors also showed high linearity, their sensitivity was lower. The 500 ohm resistor performed poorly on both measurements. This means that a 100 ohm resistor is the most effective because it is the most reflective of changes in the concentration of organic compounds, giving the fastest and the most accurate response. Next, I tackled the goal of shortening the detection time. I hypothesized that we could get a reliable result much faster by using an earlier data point from the current curve. I compared three different signal analysis methods using the peak current, Imax, the point where the current is declining at its fastest rates, which are called ID, and the lowest current, I0. Sorry. And my analysis showed that using ID provides the most favorable compromise. It maintains high sensitivity and strong linearity, but significantly reducing the testing time, bringing it down to an average of about 10,000 to 25,000 seconds, while IMAX was much faster but less sensitive. Next, I wanted to see if these optimized parameters will actually work with real wastewaters, rather than just the artificial wastewater I tested at my house. For this validation step, the electrochemical sensor was configured using the best settings from my previous trials, 100 ohm external resistance and the ID observation point to maximize both sensitivity and speed. The real wastewater samples were collected from a municipal treatment plant in Huaiyan, Xinjiang, China. To test how well the sensors could track different organic concentrations, I looked at three matrices. The raw wastewater labeled as 1 sharp, a 1-fold dilution as 2 sharp, and a 2-fold dilution as 3 sharp. Finally, parallel standard chemical oxygen demand, or COD, tests were conducted alongside our BODQ to establish a reliable baseline that I could compare our results against. As you can see in graphs A and B, the measured BODQ concentrations decreased proportionally across the three samples, perfectly matching the trend of the standard COD tests. This proves that our sensor can accurately track changes in organic load, even in complex real-world mixtures. And more importantly, graph C shows the BODQ to COD ratio, which we use to evaluate sample biodegradability. In wastewater treatment, a ratio of 0.3 is the critical threshold. Our sensor successfully showed that the raw wastewater safely exceeded this 0.3 threshold, while the diluted matrices accurately fell below it. Ultimately, this provides that the optimized MFC sensor reliably evaluates complex real wastewaters. And next, I'll move on to the discussion. This investigation has shown that microbial fuel cell sensors are a very promising and viable tool for the rapid detection of BOD. Through my experiments, I determined two key optimizations. First, the most effective external resistance for achieving both high sensitivity and linearity is 100 ohm. And by using the point where the current declines at the fastest rate, ID, as an observation point, we can find an optimal balance that reduces detection time without sacrificing the accuracy and reliability of the results. And by considering these results as optimal, real wastewater tests confirm that the sensor is highly accurate and represents a reliable and rapid method for practical environmental management. Finally, I'll move on to the acknowledgements. I would like to extend my sincere thanks to my mentor, Dr. Shan Qi at Tsinghua University, for his invaluable guidance throughout this project. And also, I had a chance to visit the Kawasaki City Sewage Bureau in Japan to have a better understanding of the key role of wastewater treatment plants. This will be the end of my presentation, and thank you for your attention.